the combined gas law, also known as the universal gas law. I tend to call it the combined law, but I've seen other places call it the universal gas law. What do we do when neither temperature nor pressure nor volume is held constant? In all of the examples we've done so far, pressure was held constant, or volume, or temperature was held constant, or sometimes both. For Avogadros, or moles were held constant in other cases. And so, what if none of those things are really remaining constant except moles? Then we need not the Charles law or the combined law. I'm sorry, not Charles or Boyle's, but the combined. And here's what it looks like. Pressure at the beginning times the volume at the beginning times the temperature at the end equals the pressure at the end times the volume at the end times the temperature at the beginning. P1 V1 T2 equals P2 V2 T1. And temperature is the weird one, of course, so that's how you can remember that. Now, another way you can remember it is do this. What if we go in here and we cover up some things? What if we get rid of the T's? Why would we get rid of the T's? Well, T's don't matter if the pressure is constant, right? So T's don't matter if the temperature is constant. So if the temperature is constant, those T's just divide out. They don't change, they don't affect anything. And look, we've got Boyle's law. Constant temperature gives you Boyle's law back. And let's put the temperatures back in. What if this time we have constant pressure? Let's get rid of the pressures. Pretend that the pressures don't change, so the beginning and end are equal, so they divide out, and we've got Charles' law. So really, if you know combined law, you don't really need Charles or Boyle's. You can do it all in one step if you're clever enough to ignore the things that's not changing. So how do we use a problem? How do we do a problem like this? Here'd be an example. We have a gas, blah blah blah, yada 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 yada. So here we go. We have a gas with a volume of, I'm just tired of saying it. Oh, too tired to speak. So here's what I'm going to do. Let's go ahead and, I've been kind of, I don't know if you noticed, but I'm stalling because I know it's going to take you a while to write that whole problem down. Do some manipulations while I'm waiting on you. Okay, a gas has a volume of 250 cc at 250 K and 25 psi. What temperature is required to give it a volume of 550 cc at standard pressure? And so we start figuring out what to do. Now, this is a combined law video, so we know that we need to use the combined law, but what if we didn't know? Well, we go through, with all of these problems, we go through and we label, we look at the units and see what we have. So, we have 250 cc's as our volume. cc stands for cubic centimeter, same thing as a milliliter, so we've got to recognize the cc as a volume, that's our volume at the beginning. 250 K, that's Kelvin, that is our temperature at the beginning. 25 psi, psi is a pressure, that's our pressure at the beginning. What temperature, I'm going to circle that in a different color because that's the thing that we want at the end, that's the thing we're trying to find, T2, is required to give it a volume of 550 cc's. That is our volume at the end, and standard pressure is our pressure at the end. So, if we look at this, we don't just have T's and V's, we don't just have P's and V's changing, we have everything changing, and that's how we know that we're going to need to use the combined law. So, let's go ahead and let's do it. What's the pressure at the beginning? Well, that's the nice thing about going through and doing what we did in circling and labeling things. We can just plug them in now. P1 is 25. V1 is 250. T2, be very careful, this is where people screw up here. They'll put this 250 in. That's not what we want. We want temperature at the end. Temperature at the end is what we're actually being asked to find. We don't know it. So we've got to leave that as a variable. Equals pressure at the end, which it says is standard, so we can use anything we want. Well, not really, because we need to make it match our earlier pressure, which was in psi. So we're going to, what is standard in PSI? That's 14.7. So that's P2, V2, 550. We got to check, is that the same unit as we used before? CC. Yes, it is. So even if you don't know what a CC is, you can still do this. It's a cubic centimeter. It's the same thing as a milliliter, but you don't even have to know that. T1, temperature at the beginning was 250 K. What do we use for temperature has to be in Kelvin, and it is. So we don't have to change that. That was convenient. So now I'm going to solve that by getting the T2 by itself. So what I want to do is I want to divide out. I'll show you the fastest way to do this. I wouldn't multiply any of these. I would just, we're going to divide those out by dividing by 25 divided by 250. And then we're going to divide by 25 and divide by 250 on the other side. Now whenever I see 250 in two different places, I wonder if I miscopied something down. But if I look up here, I have 250 Kelvin and 250 cc. So those are the same value, but they are different things. So one of the nice things about that then is I can actually just cancel those out, and I don't need to include them in the calculation. So now I can just take 14.7 times 550, and then I'm going to divide it by 25. So I'm finding T2, so what I'm about to find is a temperature. Yes, Yes, Mrs. Patterson, please do that. We have T2 is 323. I believe we can only justify 2 sig figs here, so we're going to go 320. 320. And the unit we plugged in was, for the temperature, was Kelvin. So your temperature will always be in Kelvin. Now, if the problem does say to give Celsius as an answer, you have to do that, but you don't work the problem in Celsius, you work it in Kelvin, and then when you're done, you subtract 273 to get the answer. So if this were asking for the answer in Celsius, we would now, and only now, subtract 273 and get an answer of, what's that, 47. So, that's it.